going to explain difference of squares, factoring pattern, and a polynomial multiplication pattern. Difference of squares, the acronym DOS, is oftentimes used to describe a difference of squares. Difference of squares is a product of binomial conjugates. And to tell you what that means, I have binomials, and I'll start each one with 2x and 2x, and then I will end them with 5 and 5. But the trait that makes them the conjugates, notice that everything is the same at the moment. The trait that makes them the conjugates, one binomial contains addition, the other binomial contains subtraction. When I take the product, I'm going to have 4x squared minus 10x plus 10x minus 25. Notice that the linear terms are additive inverses, so that when I combine like terms, what I'm going to have left is 4x squared minus 25. And we need to take a minute and talk about variables raised to powers and how you determine if a variable raised to a power represents a perfect square. When you have a variable that's raised to an even power, that represents a perfect square. That's your perfect square. And the reason why, going back to exponent properties for just a minute, if you have x cubed times x cubed, you're going to add the exponents together, and that's going to result in x raised to the power of 6. If I have x to the 4th times x to the 4th, that's going to result in x to the power of 8. When you think about what a perfect square is the product of a number times itself. And in the examples that I've written here, I've got the same variable, same power, times itself. So that is the definition of a perfect square. Let's do one more. X to the 5th times x to the 5th is going to result in x to the power of 10. So if the exponent is raised to, or if the variable is raised to an even power, or if the exponent is even, then that qualifies as your perfect square. Let me erase this and let's get back to what we were actually talking about. And I'm going to clean up my board and then write my product. So this results in 4x squared minus 25. Let's analyze the pieces. The quadratic term is a perfect square. So here's my quadratic term, noting that 4 is a perfect square and the exponent is even. So that qualifies as a perfect square monomial. The constant is 25. 25 is a perfect square, 5 times 5. And even though 25 is negative, the negative represents subtraction, and that's why these are called difference of squares. Difference is associated with the operation of subtraction. So I have two perfect squares connected by subtraction, which is why this is called a difference of squares. And the linear term always sums out the problem. The linear terms end up being additive inverses, so the linear term is always 0 in these little patterns. I would like to look at a few of these with you, and I would like to look at taking the products, and then I would like to look at it in the reverse to help you recognize when you're viewing a perfect square binomial or a difference of squares binomial. And let's see, let's look at number 13. Not everything on this sheet represents a difference of squares, so I'll just do a few just to give you the idea. Let's look at number 13. So I'm first going to calculate 49k squared, and then I'm going to have negative 21k plus 21k, and it's going to end with negative 9. So as expected, the linear terms are additive inverses. They will sum to 0, and what's going to remain are two perfect squares connected by subtraction. So I'm going to have 49k squared minus 9. To analyze the pieces, perfect square, even power, perfect square connected by subtraction, which is why it's called a difference of squares. Now let's do one more, and then let's analyze looking at it in the reverse. Maybe let's do number 25. So number 25, I'm going to start with 36a squared, and I'm going to have I have two variables here. And let's see, so my linear term here is going to be 42ab, and then the partner linear term is going to be negative 42ab, and then the last term is going to be negative 49b squared. And as always, the terms in the center, not really linear terms, but the terms in the center are going to sum out of the problem, and what's going to remain are two perfect squares connected by subtraction. So notice here, I have a perfect square in 36, I have an even power, which justifies as a perfect square monomial, and I've got 49, which is a perfect square, b squared, an even number, connected by subtraction. So even though it's not a quadratic, it still represents that difference of squares pattern. And let's look at it in the reverse. Looking at it in the reverse, going down here to one of the puzzles, and this is as good as anything. Notice the row right here, looking at the perfect squares, going in the opposite direction. So notice here, even power, perfect square, even power. 1 is a perfect square, 1 times 1. Notice here I've got all perfect squares. And if I'm going to try to untangle this and match this up, the way that I could think about this in the reverse, well, n squared is a result of multiplying n times n. 49 is a perfect square of 7. And I know that since the linear term is 0, that means one operation is addition, the other operation is subtraction. And let's do letter H. Let's analyze letter H. So I know that 4n squared is a result of 2n times 2n. And I know that 9 is the product of 3 and 3. And since the linear term is 0, the term in the middle is 0, that's my cue that my binomials have the alternating signs. And let's look at the last. Let's look at E. 144 is 12 times 12. And 25n squared will be the result of 5n and 5n. And since the linear term is 0, that means one operation is addition, the other operation is subtraction.